Hi, and welcome back to another Covid-eo. My name is Ioana Bouros, and in the previous video in this series, we have seen how compartmental models relate to a given population. But how does one go about applying this theory to epidemiology? In the context of an infectious disease, an individual can either have not contracted the disease, so they are part of the S susceptible compartment, be currently infected, so they are part of the I infectious compartment, or has already recovered. This is what is known as the SIR model, and individuals move between these compartments at given rates, beta and gamma. The SIR model assumes that the population is well mixed, that is, any susceptible can come into contact with any infectious individual. As you can imagine, for large, spatially inhomogeneous populations, this assumption might not be entirely reasonable. Moreover, the model considers that no one is dying, either due to the epidemic or of natural causes. There are no births replenishing the susceptibles, and no movement of individuals from the recovered compartment back into S as a consequence of immunity loss, making this model appropriate only for short-term predictions and for infectious diseases where people do not lose immunity. Unfortunately, for COVID-19, this is not the case, so this type of model is not appropriate without some changes in our understanding of the epidemiology of COVID-19. When using the SIR model, we would usually start with most, say 99% of the population in the susceptible compartment, and the rest of 1% in the infectious one. These are what is known as the initial conditions of the model. The ODE system of the SIR model is then written as the S over dt equals minus beta Si, the I over dt equals beta Si minus gamma I, and the R over dt equals gamma I. We have this expression for the rate of transmissions between the S and I compartment because at all times the number of new individuals that can become infected depends on both the number of individuals that can infect and those that can be infected. The advantage of this model is that it is very flexible and easy to configure. For example, we can consider an exposed compartment for the individuals that have caught the virus but are not infectious yet. Or we can start differentiating between asymptomatic, symptomatic, superspreaders, and non-superspreaders infections. Which means we just have to add more compartments. However, whilst the model can be made more complex to incorporate more nuanced epidemiological processes, this comes at a cost. More compartments mean that we need to make more assumptions about the processes at play. For COVID-19, people really relied heavily on the SIR models because early observations about the virus strongly indicated that there is a non-negligible time period in which individuals do not manifest symptoms. This is an example of why this approach is a very powerful and easy-to-use tool. In the next video, we will look at an actual model used in modeling the COVID pandemic by Public Health England. Thanks for watching.